This lesson is for section 1.7 in our textbook, Symmetry and Graphs. We've got three main objectives for today. We're going to use symmetry so that we can graph a little bit quicker. We're also going to use algebraic tests to determine the type of symmetry of different graphs of equations. And our final objective, we might not get to it in this particular video, it just depends on how long it goes. We're going to complete the square to right equations of circles in standard form. First up though, we're going to talk a little bit more about symmetry and reflections and give you some background information. Alright, so we say that 2 points are symmetric with respect to some line L if the line is the perpendicular bisector of the segment that joins those points. So let's say we connected points A and B here. A and B are symmetric to one another if and only if that line L here is the perpendicular bisector, meaning it's both perpendicular to that segment and it bisects that segment. So now we can say with with certainty that points A and B are symmetric to one another with respect to the line L. Okay, now let's say I asked you to reflect this particular semicircle about the x-axis. I'm sure that all of you would give me the correct picture and you would graph something like this. Now, what I really want to pay attention to is what's happening in this picture. So let's say we take any of those particular coordinates here, which I'm going to label x, y. Anytime we reflect that over the x-axis here, now these points, that's a terrible semicircle, but now these points become x comma negative y. Okay, this is really important. This is what we're looking at algebraically. So the point xy becomes x negative y when we flip something over the x-axis. Now, when we reflect over the y-axis, this semicircle here, let's take a look at all the points x comma y. Now when we reflect over that y-axis here to get this picture here, now those coordinates become negative x comma y. Okay, so we started with the points x, y. Now all of those points reflect over that y-axis to become negative x, y. Now, for our third and final reflection, we're going to talk about a reflection about the origin. This might be one that you're not familiar with, but basically all that a reflection about the origin is a reflection over the x and the y-axis both, okay? It really doesn't matter the order. I'm going to go in order of reflecting over the x and then the y, but if you did the y and then the x, you would still result in the same picture. So this red semicircle has been reflected about the origin to produce this blue semicircle here. Okay, let's see how it started. So we've got first our red semicircle here reflected about the x-axis first, and then we'll reflect it over the y-axis, and that's why we have that resulting picture. Okay. Now once again, I want to pay attention to the coordinates here. If we go back to this original picture here, we started with the coordinates x, y. Now we're going to end up with the coordinates negative x, negative y. So every point here on this semicircle will be found over here as the coordinate negative x, negative y. Alright, so coming back to our note sheet now, if I ask you to sketch the reflection of some point A about the x-axis, that means I'm going to take this coordinate 2, 1, and after I reflect it over that x-axis here, let's call that A prime now. Now those coordinates are 2, negative 1. So as you can see, like we talked about before, the point xy becomes the point x, negative y. So xy becomes x, negative y when you're reflecting about the x-axis. Now if we take our point A and we reflect that over the y-axis, now that point has coordinates, let's call it A prime once again, coordinates negative 2, 1. Okay, so as you can see here, the point xy becomes negative xy when you're reflecting about the y-axis. So xy becomes negative x comma y. And finally, if we take our point A and we reflect it about the origin, that means we're first going to reflect it over the x-axis and then the y-axis here. So I'm going to write that as A prime here. And so let's take a look at our new coordinates. We have the point 2, 1, which now becomes negative 2, negative 1. So as you can see here, the point xy now becomes the coordinate negative x, negative y. Okay, so xy becomes negative x, negative y when we reflect about the origin. Alright, now using these three new rules that we just looked at, I would like you guys to try this example here on your own and check with the key. So please don't graph this. Try to use these rules here to answer A, B, and C. Alright, now in this particular section, you're going to be given all sorts of different equations and you're going to be asked to determine if there's any symmetry for the graphs of those equations. Now in each of these pictures below, you're seeing a different type of symmetry. Okay, so this first example here, this is clearly not a function. Okay, it doesn't pass that vertical line test, but it still does have symmetry with respect to the x-axis because as you can see, every single point on the graph of this particular equation here it's reflected over that x-axis, so you see the coordinate x, negative y. So we would say that this has symmetry with respect to the x-axis. Now, in our second picture here, you can see that this is definitely a function. Okay, it's passing that vertical line test. But what we also see is that when a function is symmetric with respect to the y-axis, for every coordinate x, y that you see on the graph of that function, you're going to find the point negative x, y as well. So if we see something like 2, 6, and we know that this function is symmetric with respect to the y-axis, we know that that graph here has to contain the point negative 2, 6 as well. So it's really important, I know I'm repeating this again, but it's really important that you understand what's happening to the points in something that's reflected over the x or y axis. And then finally, when we look at when something, again, this is a function as well, when a function here is symmetric about the origin, we see that for every point x, y that lies on the graph of that function, you'll see the point negative x, negative y. Now later in the semester we're going to talk more in depth about this, but whenever we see a function that is symmetric with respect to the y-axis, we call that an even function. And whenever we see a function that's symmetric about the origin, we call that an odd function. So this isn't something quite yet that we're going to use in this particular section, but we will talk about that very soon. Now, one of the things you will be asked to do in this particular section is we're going to give you equations, and we're not going to provide you with the graphs of those equations. And without looking at a graph, you have to determine what type of symmetry the graph of that equation would have. So there's actually algebraic tests that you can perform in order to determine what type of symmetry the graph of that function or equation might have. So if you want to test to see if there is symmetry with respect to the x-axis here, okay, you are going to plug in negative y. Now, to see if you have the graph of an equation or a function that is symmetric with respect to the y-axis, you're going to plug in negative x into the function, okay? And then finally, if you want to test to see if your function is symmetric about the origin, then you're going to plug in negative x and negative y into your original function. So I'll tell you exactly what you're going to be doing here with these next few examples. All right, so in these examples, we're asked to decide the type of symmetry that occurs in the graphs of each of these equations. So let's start off with this first example here. Now from 90s, you did graph these types of relations. This would be a parabola that opens up to the right, shifted backwards 4 units. So this would be the coordinate negative 4, 0. Now some of you might not remember how to graph this, and that's okay. You don't actually have to know how this is graphed. You can test algebraically to decide the type of symmetry. Now from here, it looks as if this is symmetric with respect to the x-axis. And remember, our test, this is, let me just write them underneath so you can see it. This is the y-axis and this is the origin. So our test to decide if it's symmetric with respect to the x-axis is to plug in negative y. So what we're going to do in this original equation here, we'll plug in negative y into that equation. If we result in the exact same equation, then that means it is definitely symmetric with respect to that particular axis. So in this case, do you see how we have the exact same equation once we plug in negative y here as the original? That means this is symmetric. Sorry about that, my dogs went a little crazy and they still kind of are. Anyhow, so this is symmetric now with respect, actually I'm going to write WRT with respect to the x-axis. Now, let's say we wanted to test symmetry with respect to the y-axis. Clearly, you can see it's not symmetric with respect to the y-axis. So let's see what happens when we try to test this, okay? We're going to plug in negative x back into that original equation. We have something that looks like that. Now, this is not the original equation, right? It does not result in the exact same equation. That's how we realize that this is not symmetric with respect to the y-axis. Now, from our graph, we can also see that this does not look symmetric with respect to the origin, but just to show you what that would look like if you were to verify this algebraically, now we're going to test that third test here. We're going to plug in both negative x and negative y. So if we do that, we have negative y squared is equal to negative x plus 4. So if we go ahead and simplify all those signs, we're left with an equation that does not look exactly like the original. So as you can see here, we can tell that it is clearly not symmetric with respect to the to the origin. Okay? All right, now for B, once again, this is another parabola. This time it opens up. It's shifted down 2 units. So I'm just kind of briefly reviewing these graphs. If you don't know how they're graphed, don't worry too much, because again, you can always test this algebraically. So let's verify that this is definitely symmetric with respect to the y-axis. So we're going to plug in negative x here. When we do that and we simplify, we end up with y is equal to x squared minus 2, definitely the original equation. So now we can see that this has symmetry about the y-axis. So it's symmetric with respect to the y-axis. Now you'll see that if you try to test if it's symmetric with respect to the x-axis by plugging in negative y here, you will end up, once you solve for y, you'll end up with an equation that has the exact opposite signs here for x squared and negative 2. It's now negative x squared and positive 2. So what we're seeing here is that it's not symmetric with respect to the x-axis. Okay? And then finally, if we try to verify that it is not symmetric with respect to the origin, this test by plugging in negative x, negative y, that would also fail. I'll just do it real quick. So we have negative y is equal to the opposite of x squared minus 2. Once we divide out that negative 1 and we simplify here, this becomes positive x squared, but once we're dividing out that negative 1, it'll switch that sign, and our sign here, negative 2, will also switch. Okay? So it's clearly not symmetric with respect to the origin. So it's, again, just verifying algebraically. So you may have to test all three. Unless you know what the graph looks like already, then you can test and just verify the one that you think it is. All right, let's try C here. Let's say I have absolutely no idea, so I'm not even going to start off with a graph. So let's first test if it's symmetric with respect to the x-axis. We'll plug in negative y here. And when we solve for y, we end up with an equation that is not the same. So it is not symmetric with respect to the x-axis. Okay, so no symmetry about the x-axis. Let's try now the y-axis. We plug in negative x here. And we end up with negative x cubed plus 4x. And once again, not the original equation. So far we have no symmetry. If we try to see if it's symmetric with respect to the origin, we'll plug in both negative y and negative x. And we'll go ahead and simplify here. Okay, so here this is going to become negative y equals negative x cubed plus 4x. Once we divide out that negative 1 here, we end up with positive x cubed minus 4x. Here you'll notice that that is exactly the same as the original equation. So we have symmetry with respect to the origin. Okay, that's the only symmetry here for example C. Now I would like you guys to try example D. You probably know what this graph already looks like, so you can guess on the type of symmetry, but make sure you're always verifying algebraically. So go ahead and check your answers with the key. All right, we're going to do one quick calculator example and then we'll move on to circles. Now in this calculator example, we're given this function here, and at first we're just going to graph it in the standard viewing rectangle to see the type of symmetry we have. So here we go. Here's our picture. Now some of you guys might be confident here and say that it is symmetric with respect to the origin, because if we look at this portion of the graph here and we reflect it over the x-axis first, then it would be kind of down here somewhere, and then if we reflected it once more over the y-axis, it would definitely look like it would be placed over here. Same thing goes for these portions of the graph. Now, if you're not really confident, obviously, we always want you to algebraically verify, but you can also kind of zoom in on your function a little bit. So I'm going to do that now. I'm going to take my window here and I'm going to adjust it so that I'm looking at this particular viewing rectangle. So I'm going to go from negative 2 to 2. And my x scale is going to remain 1. So when I graph this now, I can get a little bit clearer picture. So once again, it looks like we have symmetry here with respect to the origin. So let's go ahead and try to test that. So here's the really important part that's easy to forget. When you decide if it's symmetric with respect to the origin, you have to plug in negative x and negative y into that function. Okay, so I'm repeating it over and over because hopefully you'll memorize it after today's video. So we have negative y is equal to 1 over negative x cubed minus negative x. Now I'm going to go ahead and just simplify some of these signs. So I have negative y is equal to 1 over negative x cubed plus x. Now at this point, I'm going to multiply by negative 1 on both sides. Okay, so let's see. Now in the denominator here, I can apply that negative so that I have 1 over positive x cubed minus x. And as you can see here, this is that original function that we started with. Okay, so it is symmetric. It is symmetric with respect to the origin. And if we try to test any other types of symmetry, those symmetries will fail. For example, if we wanted to test if it's symmetric with respect to the x-axis, we have to plug in negative y. So we have negative y is equal to 1 over x cubed minus x. Once you multiply by that negative 1 on the other side, you'll end up with negative x cubed plus x, which is not the original equation. Okay? All right, so I know we've done a few examples of this. Maybe it's overkill, but I just want to make sure that you totally understand how to test algebraically the type of symmetry that occurs from the graph of an equation. All right, let's move on now to circles. So up at the top here, I've got the standard form of an equation of a circle written up here. We have x minus h squared plus y minus k squared equals r squared, where the coordinate h comma k would be the center, and r is the radius of that circle. So C stands for center. Now, most of this should really come back to you from last year in 90s. So let's go ahead and start with example 1. It says find the equation and graph the circle with diameter endpoints negative 4, 1, and 0, 5. So we've got a point, if I just sketch this out real quick, we have a point here at negative 4, 1 and a point over here at 0, 5. These represent the endpoints of the diameter of the circle. So one of the things we need to do is figure out exactly where that center of the circle is. So I'm just going to draw an imaginary circle here and just roughly sketch this out. Well, that center is definitely the midpoint of the endpoints. Okay, so we're going to find the midpoint between those 2 points. So negative 4, 1, 0, 5. We'll add our x values, cut them in half. We'll add the y values, cut those in half, and we end up with the coordinate negative 2, 3. So now we've just found our h comma k. Okay, negative 2, 3 would be our center. Now we also have to find the radius so that we can plug that right back into our standard form of this equation here. So what we'll have to do is find the length of our diameter. You can also find the length between the midpoint to one of the endpoints. That works as well. It really doesn't matter. Just make sure you remember which one you're finding, okay? Because a lot of times students will cut something in half when they shouldn't be. So we're going to go the full diameter here and find that length. So we'll find the distance here. Now when I do distance, one of the quickest ways for me to do this without having to write out all of the equation here, I take a look at the x values and I see the overall distance in terms of a number line. This is 4 units away, right? So if I take that and I square that first term, that would be just like taking negative 4 minus 0 squared. That's actually what I would get, 4 squared, right? It's equivalent to each other. And if I do the same thing with the y values, 1 and 5, the overall distance between these two on a number line is only 4 units. So I'm going to add another 4 squared here. So if I take the square root of 16 plus 16, which is the square root of 32, I would get 4 root 2. This is the overall length of the diameter. Now, if you're not sure why I'm doing it like this, which is it's just a quick little trick that I do to find distance, you can obviously just use normal distance formula. So the next term that you would have is 1 minus 5, the quantity squared. And once again, you can see that this is going to be negative 4 squared, which is the same as 4 squared. So I just like looking at the overall distance between the points, and I do it in my head a lot quicker than actually writing out distance formula. Okay, so that's just a trick that I use. You're more than welcome to use it or not use it. Now, if 4 root 2 is the diameter, that means 2 root 2 would be the radius. So now when I come back to the original standard form here, and I want to write this in standard form, I start with x, then I subtract the h. Remember, this is h comma k here, negative 2, 3. So I'm going to actually add 2, because it's x minus a negative 2. We'll square that, plus y minus 3 squared equals this radius squared. So I have to make sure I square both parts. A lot of small mistakes happen here when people don't remember to square both parts. So we end up with 4 times 2, because we square the 2, we square the root 2 to give us 8. Okay, so this here would be the the equation of that circle in standard form. Now we can go ahead and graph this. So we just go to negative 2, 3. This is obviously the very easy part. When you're estimating this radius, because it's going to be kind of tough to graph accurate points here, it's okay if you don't have it super, accurate. You can just kind of estimate to graph this circle. But normally what we would do is just go up, right, down, and left the same number of units of the radius. But since this is kind of a goofy radius, 2 root 2, you can just sort of estimate that distance up, down, left, and right. So there is our graph, and we can move on now to example 2. All right, in example 2 it says a circle is tangent to the lines y equals 2 and y equals 8. So I'm going to go ahead and just kind of graph these in here. It's 2 horizontal lines, one up here. We know that our circle touches each of these lines here only once. That's what it means to be tangent. Okay, that's a review of just a term from geometry. So if it's tangent to these lines, then it's got to lie inside these two lines, inside this region here. Now, if the center is supposed to go through the line x equals 5, okay, then that means we have one clue as to what the center of our circle actually is. So we know that h comma k is our center, so right away we know that we have the coordinate 5 comma something for the center. So let's try to figure out what k would be. Well, if this is placed between the two horizontal lines 2 and 8, that means this overall vertical distance here is 6 units. So that means that this coordinate here would be at 5 comma 5, or I'm sorry, 2 plus 3, so 5 comma 5. Now obviously from the graph it's really easy to tell because we're lining right there. But if you were not given a graph and you just had to sketch this out, you would just take this bottom equation, which is at y equals 2, and add 3 units vertically to the y coordinate here to get 5 comma 5. So that's where our center is at. Now for the radius, since we know that that overall distance here is 6, that means the diameter is 6, and our radius would be 3 units long. Okay, so now we've got r is equal to 3, and we can go ahead and write this in standard form. X minus 5 squared plus y minus 5 squared equals 3 squared, which is 9. Now at the bottom here, I do have a note that talks about how to graph this type of equation here on your calculator. And one of the things that you can do here is solve for y in order to get two different functions. So I'm going to solve for y real quick. I would first subtract that x minus 5 to the other side. Okay. Now I'm going to solve for y by square rooting both sides. So I have y minus 5 is equal to positive or negative square root of negative x minus 5 squared plus 9. Then I'm going to go ahead and add 5 to the other side. So I have 5 plus or minus square root of negative x minus 5 squared plus 9. So you can see here that we have two different equations. Now the first equation here, we just isolate 5 plus the square root of negative x minus 5 squared plus 9. That would only give us the top half of that circle. It's going to give us the top half of our semicircle. So if we were to graph that, it would only appear like that. Once we plug in the other line here, which would be y equals 5 minus the square root of negative x minus 5 squared plus 9, this would give us the bottom half of the circle. So that would complete the circle like so. Okay. Now one thing you're going to see though in your calculator is that when it gets to trying to graph right here, it can't do it. It leaves a space. There's not enough pixels in your calculator to do that. So I would like you guys to just try that. Plug it into your calculator, see what you get. You should get a nice little circle here with a gap between those two semicircles, kind of like that. Now at first when you graph that circle on your calculator, it probably won't look much like a circle. In fact, it'll probably look like an ellipse. And that's because what you need to do is set your window to zoom square, and that way it'll really make the shape look like a circle if you set it to this correct setting, zoom square. All right, last up, we're going to just complete the square on one of these problems. I'm going to just do example 3 here. This is right now the equation of a circle, and the reason why I know it's a circle is because I have two quadratic terms here, okay? Both of them are also positive, and they are the same constant. So that's how I know I'm dealing with a circle and not a hyperbola or an ellipse, okay? So what we're going to do is rewrite this in standard form. We want it to look like this: x minus h squared plus y minus k squared equals r squared. So what we're going to do is actually complete the square so that we can get it to look more like this. So we're going to just follow these steps here off to the side. The first step here says move the constant to the side with y, or just where it's 0 on the other side. Okay, so we don't have a y here, but let's pretend like that had been a y. It's the same idea. So we can move this constant, the 15, to the right hand side. So we have 16x squared minus 8x plus 16y squared minus 64y equals 15. Now we're going to factor out the quadratic coefficients for both terms, both the x squared and the y squared. So if I factor out a 16 here, I'm left with x squared minus 1/2 x. Okay, and if I factor out the 16 here, I'm left with y squared minus 4y. Now at this point, we're just going to complete the square. Remember, we cut that linear term in half and we square it. So in this case, I would have x squared minus 1/2 x plus 1/4. Okay, oh, I'm sorry, 1/16, because we have to cut 1/2 in half, so that'd be 1/4, and then we square that to give us 1/16. My bad. Okay, now for the next term, let's do this one in red. we cut that 4 in half and square it. So 4 cut in half is 2. Square it, you get 4. And here comes the part where students will make the most mistakes. Make sure you balance your equation. So on the left-hand side, what we actually added to this equation is 16 times 1/16. So we have to add 1. And then from the second portion here, what we actually added was 16 times 4, which is 64. All right, so now when I rewrite this, I have 16 times x minus, remember this is just 1/4. It's what you cut in half that's always going to be this term here. So x minus 1/4 squared, this is this term above factored. And we have plus 16 times y minus 2 squared equals, on the other side here we have 80. Okay. Now from here it's getting really close to looking the way it's supposed to. The only thing we are missing is the fact that in front of these terms, these binomials, we have a 1 out in front. So we need to get rid of this 16. So in this step, we can divide by 16 on both sides of the equation. And we're left with, I'm going to write it underneath here, x minus 1/4 squared plus y minus 2 squared equals 5. All right, so as you can see, the center would be 1/4 comma 2. And the radius would be the square root of 5. So I know I went through that one pretty quick. We'll do the next couple examples in class together. All right, nice job. I'll see you guys tomorrow.